Welcome to Module 1.5. So now we are going to talk about runtime defenses against control hijacking. So there are a number of different solutions provided in the last 10-15 years for runtime checking. And to do runtime checking, of course, you have to insert specific code into your program so that runtime checking is possible, right? Now, in order to do that, you don't want to do it manually, so you want real automated way of inserting code that will do some checking. And the first example of such a system is StackGuard. So StackGuard is actually a method by which instead of having this stack frames organized the way we described before, between local variables and the return address and the function pointer and so on, there is a specific set of bits that are inserted, and they're called canaries. So canaries are sort of like, if you put say sand at the threshold of your door, then anybody who enters your room has to go through this threshold and have his or her footprint on the sand. And that's the idea, that if there is an overflow, then it has to overwrite the canary first before it can go and overwrite the return address or the frame pointer and so on. So therefore, canaries are put into the stack frame for every function call, and this is done by modifying the compiler. So there are two types of canaries. One is called a random canary, another is a terminator canary. So in the random canary case, you want to choose a random string at the startup of your program and then use that canary string into the stack frame. So every time a function call happens, between the local variables and other content of the frame, you put the canary. And then before you return from the function, you do some work, and this work is basically to check that the canary that you had put in is intact. If canary has changed, then probably you are going to get, that somebody has tried to overflow the buffer, or it has happened because of bad input. And if the canary has changed, then the program is exited. So therefore, even if you don't succeed, you can still create a denial of service attack by doing this, but at least you are not executing malicious code. Now, the attacker, if he can guess the random string, then of course he can create the input in such a way so that during overwriting, the canary will be overwritten by itself. But if you change the random string often, at least at the program startup every time, then it's difficult for the attacker to actually guess the random canary. The terminator canary is when you put a termination character into the canary. So therefore, even if the attacker learns the canary, he or she really cannot use it, because as soon as he creates a string in which he puts a string terminator character, then while copying onto the buffer, only up to that point will be copied. So therefore, his overflow will not succeed. So StackGuard is basically designed to do this, which is before every function call, it adds a few instructions, machine instructions, to add the canary, and before the function returns, it adds a few instructions to check the canary, and that's what is done by using a GCC patch. So it's I think GCC 2.8.1 onwards, this is there. And then there is a performance overhead because you are adding few instructions for every function call before and after, prologue and epilogue as they're called, and therefore there will be during execution you will have an overhead. Now for small programs or not very long-lasting programs, the overhead would be much. But in case of very long-lasting programs, as was shown for Apache, it was only 8%. So that's if your program is critical and you don't want to be attacked by buffer overflow, then you want to use that. Now canaries do not provide full protection, so it's not 100% solution. As we pointed out, that if you can guess the canary, for example, then you can actually overcome this defense, and canary will remain unchanged and you won't detect that there has been a buffer overflow. And then for heap protection, this doesn't work. So you have to do something else, and there is another system called point guard that was designed to actually do the function pointer and set jump buffers and so on by encrypting them with XOR, XORing with a random string, and in this case the effect on the performance seems to be high. So then IBM took over this stackguard idea, and then from GCC 3.41 onwards, if you use -f stack protector as your compiler flag, then you can do something more than just canary, and this is called propolis. And the idea here is that you want to protect the return address, you want to protect the stack frame pointer, and the canary is supposed to protect an overflow there. But the other thing you can do is that you actually put the pointers and so on in, so you restructure the stack frame and you put the pointer arguments to protect function pointers, for example, and string buffers, all that stuff below the canary. So main change is that even if an argument, normally arguments should go here, but in this case you basically if you have a string, if you have a pointer argument, then you basically put them below here, and therefore even if your canary is violated and remain unchanged by some trick, you cannot actually change the pointer arguments and by doing buffer overflow. So Microsoft Visual Studio since 2003 version has kind of combined the ideas from propolis, which basically protects the pointers, and random canary idea. And so what /gs option during compilation would add this in the function prologue and this in the function epilogue. And here basically you can see that it allocates space. So remember we said that the stack grows from higher to lower addresses. So if your stack pointer is here, ESP now, then you want to make your ESP previous ESP -8, so it creates an 8-byte location, and this is where your frame pointer should point to now, that is the end of the previous frame. So now here you take this double word security cookie, and then you XOR the cookie with the content of the ESP, and then you move that into you save it into the stack. And then in the epilogue, what you are going to do is you are going to retrieve it, and then you want to check if it has remained unchanged, and then if it has remained unchanged, then you can know that it has not been violated. So, and then 2010 Visual Studio has an enhanced technique. And that is it makes it mandatory for using /gs for all functions unless proven unnecessary. So this is how this canary, so /gs basically takes the canary and separates the return address, the SFP, the exception handlers, and the string buffers, and the pointer arguments and so on. So therefore, since the strings grow on this direction, so and putting the pointer arguments here, you cannot overflow and change the pointer arguments. Now there is one technique called structured exception handler technique, by which the /gs has been shown to be defeated, which is in the exception handler, what happens is that you have a sequence of exceptions, because when an exception happens, first, if the exception matches with a certain filter, then you call a certain exception routine. Then if it doesn't match, then it goes and checks with the next one, and then it chooses that handler, and so on, and then eventually it goes to a default handler. And so each this exception record, what they call, has a handler, address of a handler, and then it has a next pointer which points to the next exception that must be checked for this to handle this exception if it doesn't match with this. So by doing a buffer overflow, one can actually change this next pointer, and if you change the next pointer and point to something that whose handler is a malicious code, is a pointer to a malicious code, then you can do an attack based on exception handlers. So what you are going to do this, how do you go about doing, getting rid of this problem? So that is something that Microsoft has done, and there are two things. One is using a safe SEH, a safe exception handler linker flag, and another is a safe exception handler OP, and in the first case, what you do is that your linker produces a binary with a table of safe exception handlers. So you know which exception handlers are safe, and so system will not jump to an exception handler not on the list. So you will, whenever you get an exception handler, you check if it is in the list. If it isn't, then the program will stop. So, but this has very high overhead. And then SEH OP, which is actually not a runtime defense, it's more like a platform defense. What it does is that during the compilation, the exception record list that we just saw here, so what it does is it does enter a dummy record at the very end of the exception handler list. Now, how does that help? The reason why it helps is because the exception whenever an exception happens, you walk through the next pointer. You use the next pointer to go from one exception handler to the next until you find the one that you want to use. So in this system, and this is from WinVista SP1 Service Pack 1 onwards, is that you actually first walk the entire exception record list and see whether the last dummy one that you know what it is found. And the reason is that most of the the structured exception based attacks actually would do a buffer overflow to rewrite the next pointer at some point in this list. So if you are attacked, and if your next pointer at some point has been rewritten, then this list has been redirected to something else. So therefore, by walking this list in the violated next pointer, you will find a path that does not go through this dummy record, and therefore you will figure out that something wrong has happened, and you will terminate the process. So that's what SEHOP gives you. So in summary, the canaries are important defense tools, and they are used most of the time, but they do not prevent all control hijacking problems. And heap based attacks are still possible, as we will see, and then integer overflow attacks are totally independent of this. And /GS flag does not itself prevent exception handling attacks. You would still need safe SEH and SEHOP in order for to turn on this either the safe list of exception handlers, or using the dummy record and figure out that exception records have been compromised. So now the previous techniques, as you saw, like if you want to use stack guard or SEHOP and things like that, all require you to recompile your code because you have to turn this on. what if you cannot recompile your code because you don't have the source or for some other reason? So then what you can do is instead of using the standard lib for various string related activities, what you do is you use libsafe, which is from Avaya Labs, and this is a dynamically loaded library. So instead of using the standard libc version of this function calls, you intercept the call to string copy and then use some checks. So this libsafe version of this code will actually have a check that checks whether there is enough space for a string to be copied. So you check the length of the string against the amount of space you have, which is the frame pointer minus destination, that length. And then if it does, then you are fine. You can copy without causing a buffer overflow. Otherwise, it will terminate the application. So this is another technique by function call interception. So you intercept the function call and replace it by some safety checks and then the actual function. So there is also stack shield, which is that basically also changes the function prolog and copy the return address and SFP to a safe location. So what happens is that when your function returns, it checks if the return address and the SFP that was copied in the beginning is still the same. If it is, then it's fine. Otherwise, it can actually figure out that there has been an overflow, and it can actually then rewrite with the original value of return or SFP, or it can actually terminate the program. And this is implemented as an assembler file processor and change GCC. Now there is another very interesting and very ongoing research area, which is control flow integrity check. And the idea is that in the beginning you do formal analysis of your program to somehow capture the control flow of your program, and then dynamically check if any place during the execution, anytime, you are going to violate this control flow that you have already discovered. Now obviously this control flow has to be compact that you have discovered, because if your program has exponential number of different paths, you cannot record that and check against that. So this becomes a little bit complex, and sometimes it also gives rise to false warning or false positives, and so if there is time later, we'll talk about control flow integrity a little more, because it's a very interesting research area. So that finishes module 1.5, which was about the basics of runtime defenses against buffer overflow and control hijacking attacks, and use of canaries and how various other techniques are used for checking whether you have violated the return address, and if you have violated the exception handler list, and things like that. Now the final module in this will actually talk very quickly about a few other control hijacking attacks, and that will be more or less what we'll cover in class about control hijacking. And of course, through your projects you will do a lot more on control hijacking, but next we'll go into other topics in the next week's lecture.